Okay, welcome back, everyone. Let me just send a attendance form. It is in the chat now. This is the fourth lecture of the course on infrared symmetries in general relativity. Are there any questions you would like to ask now? Okay, it doesn't seem to be the case. So let me start by recapping what we have done so far. So our goal in the course is to get to the BMS symmetries. So far, to achieve this goal, we discussed a little bit of group theory. In particular, some important groups were SO3, which is a group of rotations, SO plus 3,1, which is the Lorentz group, and the Poincaré group, which is ISO plus 3,1. Some things that we learned in the last class is that this group is also the conformal group in the sphere S2. SO3 is the isometry group. In S2. And this guy here, the Poincaré group, is the isometry group in Minkowski. Let me write it in this way. Oh, there's a better notation. Let's just write it as R4 with the Minkowski metric. Okay, so we saw a little bit of each of those groups. We also discussed how we consider symmetries in co-spacetime, symmetries in GR, which involved maps between manifolds. So we saw that the symmetry for some tensor T is going to be a map phi such that the push forward of T equals T itself. And in particular, this is how we define isometries. So an isometry is going to be something that does this for the metric of space-time. We also saw how to discuss these things in an infinitesimal sense by using the Lie derivative. So, for example, the Lie derivative for the metric with respect to some vector v would be given by this formula here. And an isometry, an infinitesimal isometry, would be characterized by the Killing equation, which is this equation here. The Lie derivative vanishes. While for a conformal Killing vector field, we have a slightly different formula in which we allow for the vector to have a non-vanishing divergence. And this here is going to lead to a conformal transformation. So we have these two definitions for a Killing field and for a conformal Killing field, which are going to lead us to isometries and conformal isometries. And I recall that a conformal isometry is not an isometry, it is something more general than an isometry. A conformal isometry is a diffeomorphism that preserves the conformal structure, and that is less than a diffeomorphism which preserves the metric structure. So we have these two different definitions that can be useful in different contexts and will be useful for us. So we discussed these things, and we also discussed asymptotically flat spacetimes. Flatness, asymptotic flatness, sorry. Asymptotic flatness. Here, let me grab you. Okay. And the basic constructions that we did was that we started with some spacetime mg, and we found conformal extension m tilde g tilde, which behaved in a very good manner so that we could pull infinity in. And then we would define future no infinity I plus as being the boundary of the old spacetime within the new spacetime. So we have this boundary construction, and we have that the metrics are related conformally. So we have an equation that looks like this. This is being, it's just a draft, so to speak. I'm not being rigorous in this equation. Otherwise, we would have some push forwards in here to make everything behave in the precise and correct way. So we have schematically these expressions here, and we have the property that omega should vanish at I plus, because it needs to bring infinity in. Otherwise, it is positive in M. And we also ask that the derivative of omega at square plus is not 0, because we want square plus to be a surface. We want to have square plus as a single surface within M tilde, and this surface, when we give the other conditions that we want for asymptotic flatness, will end up being just R times this sphere S2. So this is what we discussed so far, and the goal for today is to give a slightly more complicated example of asymptotic flatness. So far we have only discussed asymptotic flatness in Minkowski spacetime, which is kind of trivial. So we'll go to today to a slightly more complicated example, which would be Schwarzschild spacetime. And that also applies to stellar spacetimes, which are static and spherically symmetric, because the outer spacetime needs to be Schwarzschild. Actually, don't even need to assume staticity. If you assume that the spacetime is spherically symmetric, the only vacuum solution is the Schwarzschild spacetime, and that is a result known as Birkhoff's theorem. Birkhoff. So if you have spherical symmetry plus vacuum, then the only thing you can have is Schwarzschild. So this is an interesting example. It is more difficult than the Minkowski metric, and we will illustrate how exactly these constructions can be made. Although I won't give the full details, in the lecture notes there are references that provide a bit more of detail to this construction. So we have this here, and the other thing we're going to do today is finally get to BMS symmetries. So we will derive the BMS symmetries, which are the infrared symmetries in the title of the course. And that will require a few more constructions. In particular, we will need to discuss what are called Carolean structures, which are manifolds. It's the geometric idea of a manifold that looks like a new surface, and it will be indeed a new surface for us. In addition to this, we will go directly to deriving the BMS symmetries in two different ways. One of them, which is a little bit more global, and the other one, which is a little bit more local. So we'll have these two constructions, one that is more related to finite symmetries, while the other one is more related to infinitesimal symmetries. And that will allow us to both understand the BMS symmetries in a better way and compare them to the Poincare symmetries. So this is the plan for today. I'll start with the example of Schwarzschild spacetime. I just forgot how to write Schwarzschild. Okay, Schwarzschild. And I want to show that Schwarzschild is indeed an asymptotically flat spacetime. And to do that, we will do the following. We want to construct Schwarzschild as being asymptotically flat at future no infinity. There are better constructions because Schwarzschild actually is asymptotically flat at future and past no infinities and at spatial infinity. This is discussed in an 80s article I believe by Stecker and Hansen. But I will not go into all of these detail in here because, as I said in the last class, dealing with spatial infinity tends to be difficult. So we will deal with something simpler, which is just a synthetic flatness at future no infinity, because this construction is quite fast and quite easy to grasp. So since we want to get to the future no infinity, we need to choose which coordinates we are going to use. In Minkowski spacetime, we had this Penrose diagram here, and we could be interested in many different limits to reach infinity. So we could get t goes to plus or minus infinity at r equals constant, and that would take us either here to future time like infinity or here to past time like infinity. We could take r to infinity at t equals constant, and this takes us here to spatial infinity, but neither of this the limits we want to take. Instead, the limit we want to take is something that gets us here at future no infinity. We also have past no infinity here, but this is just the same as future no infinity, so we don't need to care a lot about it right now. So if we go to future no infinity, the limit we're taking is r goes to infinity at u equals t minus r equals constant. Now, if you want to do this in Minkowski space, in Schwarzschild spacetime, you need to be a little bit more careful. You don't really have the coordinate you want to use is not really t minus r, and the reason is because this coordinate is ill-behaved near the horizon that you have in Schwarzschild. You have a horizon at r equals 2m. The Schwarzschild metric, just as a reminder, is given by 1 minus 2m over r, this is u, plus 1 minus 2m over r minus 1, dr2, plus the angular component. So this is the Schwarzschild metric. And you can see that you have this weird behaviors at r equals 2m, because this guy vanishes and this guy diverges. These are actually just coordinate singularities, so there's nothing really problematic about them. They're just weird points in this particular coordinate system. And you have another weird behavior at r equals 0, which is a physical singularity, and the spacetime ends there. So r equals 0 is not a point in the manifold. It is outside the manifold. R equals 0 does not exist in Schwarzschild spacetime. A way to understand this is that you may remember a few classes ago in which I said that we can put different metrics in R4. And then, by then I said the Minkowski metric, and I said a stellar metric. I didn't say Schwarzschild. And the reason is Schwarzschild is not a metric on R4. The manifold, the spacetime in which you put the Schwarzschild metrics is not R4. It is actually R2 times S2. And the reason for this is precisely because you lack the origin. So what you have here is one of these r's is time, the order of these r's is the radial coordinate, and this here are the angles. So the issue I have here is that you cannot have r equals 0. So you end up with this manifold instead of this one here. So singularities are never a point in the space-time. They can actually be thought of as holes. They're something that is missing from the space-time. And in particular, the Schwarzschild singularity is not in the space-time. So anyway, to get rid of the coordinate singularity, we need to work in a different coordinate system. And a very common coordinate system is the Eddington-Finkelstein coordinate system. There are many other coordinate systems in Schwarzschild, but this here is the one that will interest us the most. And if my memory doesn't fail me, in Eddington-Finkelstein coordinates are going to define the retarded time as t minus r minus I'm guessing that it is, nope, minus 2m logarithm of r minus 2m. It's something like this. It's something like this. It's this-ish. I might be missing a sign here. I might be missing some signs inside the logarithm. I might be missing a few constants, but this is the general structure. And you need this logarithmic term to have something well behaved near the horizon. And this will also play an important role when you go to infinity, because you see, when you go to infinity, this guy here diverges. And the reason you get to this expression, another way of thinking about it, is if you consider the, okay, yeah, this is a good calculation. I wasn't planning on doing this, but this is a good calculation. Suppose we want to have new coordinates, and new coordinates always parameterize light rays in your space time. So in here, the way you derive, you get to the retarded time in Minkowski space time would be just to get labels for new coordinates that walk on Minkowski spacetime. So let us do the same thing here as an example of how we get to these expressions. We want to have a new geodesic. So we will impose that on this geodesic, we have ds2 equals 0, because this leads to a new geodesic. Also, I want it to be radial, because it's easier to work with radial geodesics. And I'll keep the angular variables in my final metric anyway. So I'm going to impose that the angular variables also do not change. This means that along this new geodesic, we are going to get this expression here, which is 1 minus 2m over r dt2 plus 1 minus 2m over r inverse dr2. So you can now rearrange this expression here, and what you're going to find will be, let me just see what is the most convenient way. It's going to be dt dr equals plus or minus, if I'm not missing anything, it's going to be this thing here. Okay, you get this expression. There might be some signs inside here that I'm not considering. Yeah, it can be a little bit weird depending on the way you do this thing. But let's keep it like this. This here will hold for r larger than 2m. Now, this is a little bit difficult to integrate, but once you integrate, you're going to find that along a new geodesic, let's say with dtdr positive, and this here means that the geodesic is outgoing, so it is getting away from the center, is getting away from small r. Then you're going to have something here that will look like t minus r minus 2m log, etc. Something like this. Again, I may be missing a few constants here because I didn't carry out this integration right now. To carry out this integration, you need a few tricks that I don't want to do alive. No, not alive. Live without the A. So anyway, you find that along a new geodesic with an outgoing new geodesic, you find that this thing here needs to be constant. We call this constant u, and this ends up being the new coordinate we use. So this is the basic construction that you need. You find what are the constants along each new geodesic, and you take these constants and use as new coordinates. So you're going to have the Eddington-Finkelstein coordinates defined in this way, and you can do the same construction for many other spacetimes. So in this case, we're going to have something like this. When you do the coordinate transformation, in my notes, I only gave directly the metric in the in the new coordinates. But if you want to do these things in more detail, you can look it up at any GR book. I think Wald does this in chapter 6, but probably all general relativity books are going to mention Eddington-Finkelstein coordinates at some point. So in this new coordinate system, which is u, r, theta, and phi, so I traded t for u because now I want to keep u constant as I take the limit as r goes to infinity. And in this new coordinate system, what I'm going to find here is that the metric is now given by this expression here. du2 minus 2 du dr plus angular stuff. So this is the new metric in this new coordinates. And of course, m is a black hole mass. And we have a few ranges in here which are important. So r is always positive, and u can be any real number. Notice, again, as I said a few minutes ago, r is positive. R is never 0 because r equals 0 is not a point in the manifold. It is not a point in space-time. Singularities do not belong in the space-time. Now, something that is particularly good for us about r not being able to be 0 is that if we now define that coordinate L equals 1 over r, which I define in Minkowski as well, then L is actually defined on all of the space-time because r never vanishes. So positive values of r are mapped to positive values of L, and we now find that L is defined everywhere. So L is a very good coordinate. It's at least just as good as r greater than 0. And using L instead of r, we can change coordinates in the metric to get something with this form here. It's going to be like this, and then we have plus 2 L minus 2 du dr plus L minus 2 ds square. So we got this expression. Oops, this here is a dl. We got this expression here, and just as in Minkowski, if we take the limit L goes to 0 from the right side, then we will still have divergences in here. The spheres at constant radius r are still going to be infinite because we didn't do any miracles. And at infinity, spheres are really big. So we need to do a conformal transformation to compactify the spacetime. And the way we do this, in this case here, will be by defining g tilde equals L square GAB, where this here is the Schwarzschild metric. So we multiply by L squared because this is going to get rid of this guy and of this guy. And the new metric we get, the conformal metric we get, is now given by minus L squared 1 minus L du2 plus 2 du dl plus ds2. So this is the conformal metric. And now this metric, this unphysical metric, can be extended across L equals 0. So we now get a new metric, and this metric is a metric in a larger spacetime, which can be extended across L equals 0. So now we can extend this metric here to real values of L. The physical spacetime, so Schwarzschild spacetime, is located only at the positive values of L. Infinity, so square plus, is located at the surface with L equals 0. And beyond this surface, we have the region with L smaller than 0 corresponds to an extension m tilde without m. So we get this general construction. And in this way, you can conformally extend Schwarzschild spacetime to understand how it is asymptotically flat at future no infinity. And then you can try to work out the other details of the proof of the definition we gave of asymptotic flatness at the last lecture, and you will find out that indeed Schwarzschild spacetime is asymptotically flat at future no infinity. Not only at future no infinity, but we could also use even more general constructions to get that it is asymptotically flat at null and spatial infinities And this is done in a paper by Stecker and Hansen, for example. But I'm not gonna get into those details here. So in this way, we see another example of a asymptotically flat spacetime, which would be Schwarzschild spacetime. And notice, of course, that we only need this construction. We only need this metric to hold in an outer region. So it's not an issue if instead of considering the Schwarzschild metric through all spacetime, you consider instead that the metric is, say a star in here. So let me make a little something. So you may have a star in the middle, and then you have Schwarzschild outside the star, because that's the only vacuum solution which is spherically symmetric. And what matters here is really the behavior at infinity, or close to infinity, which is where this conformal compactification thingy actually kicks in. Although you may need to, if you want to compute the specific value of the conformal factor omega, which in this case here is just L, but in a more complicated spacetime, it wouldn't be omega equals L inside the star, because the geodesics would behave in a different way, and you might have something a little bit more complicated. But if you're interested only in the structure at infinity, which is what we usually are interested in, then you can just stick to this. So this is the construction. And yes, I guess that gives a good example, and we're ready to start dealing with the BMS group. So our next step is now the BMS group, and we start by discussing Herolian structures. And here's the reason to do that. Consider, for example, the Schwarzschild metric we just found. So for Schwarzschild, the conformal metric we found was given by the formula just above, by this expression here, du2 plus 2 du dl plus the angular part. Now consider the induced metric on L equals 0, which is square plus. So if you take the induced metric on L equals 0, you're going to find this metric here. You see that this guy here will vanish, so we get 0 times du2. This guy here falls out of the induced metric, because when we consider the induced metric, when we consider only this manifold, then dl is always 0 within this manifold. Do you notice that dl as a differential form in the ambient spacetime is not 0, but as we when we look exclusively to the slice with L equals 0, then this guy here falls out. And we have here the angular part. So this is the metric on the on future no infinity, and this holds for Schwarzschild, but it also holds for Minkowski. And in fact, up to choice of coordinates, this will hold in any asymptotically flat spacetime. And what is curious in here is the fact that we have a three-dimensional manifold. So let me remind you that I plus is R times S2, but we have a two-dimensional metric. So we have a two-dimensional metric on a three-dimensional manifold. And how exactly can we deal with these sorts of things? And this leads to an interesting geometrical construction, which is now known as a Herolian structure, which is essentially a manifold which has a degenerate metric with a single degenerate direction. So in here, we're going to discuss these manifolds, which are, we can say, some sort of alternative to pseudo-Riemannian geometry, because pseudo-Riemannian geometry always deals with metrics whose diagonal can be written either as minus, -1, a number of -1s, and eventually a number of +1s, and stuff like that. So this is the pseudo-Riemannian case. We are now extending it to account for when we have a single 0 along the diagonal. We're not assuming that there can be arbitrarily many zeros. We assume that it can be only 1 0. And we're interested in this case of exactly 1 0. So in this case, what we're going to have is the following. Let's say that we have this manifold that I'm going to call I plus, because this is actually the manifold we're interested in. We are interested in I plus across different asymptotically flat spacetimes. And we're going to assume that we give this manifold I plus a metric, which I'm going to call H tilde AB. So yes, H tilde refers to the fact that we're taking this from the conformal extension. So this is actually the induced metric taken from the conformal extension M tilde. So we had, again, the drawing. We have here M in the middle, M tilde in here. And we are inducing a metric on scribe plus, which is this boundary, from the metric in M tilde. So we get this induced metric H tilde. Now, due to the fact that this is a degenerate metric, this has one zero direction, we will need some extra structure in this manifold. So the first thing we will need is the following. We know that there exists some vector, which I'm going to call NA, which is not zero. It is not the zero vector, but it holds that HAB contracted with NA or with NB, it's the same thing, this guy is still symmetric, is going to be zero. So HAB has a non-trivial kernel. And this is going to be an important vector for us. And it's interesting to notice that in this coordinate here, NA will be given by this vector here. It is the new vector associated with the U coordinate, which is the vanishing coordinate. So this is the basic structure we will be interested in. Okay, but this is not all that we need. So for the basic Carolean structure, we will want to have scribe plus, HEB, and NA. So we have this triple here, which is composed of a manifold, a degenerate metric, and a vector in the kernel of the degenerate metric. So this here is what we're going to call a weak Carolean structure. Sometimes I'll call it explicitly a weak Carolean structure. Sometimes I'm going to say just Carolean structure. I use both terms. I don't really remember how the literature calls the things. These structures were introduced by Duval et al. At around 2014. And I don't really remember if I saw other references that discuss this sort of structures. And they did use the terms Carolean structure and strong Carolean structure, but I don't recall if they used the term weak Carolean structure. I do find it useful to use the weak adjective in some situations, so that we make it clear that we're not referring to a strong Carolean structure. So you can use the term Carolean structure for both scenarios, and I like to sometimes use the weak adjective to make it sure that I'm talking about the weak Carolean structure. So if we have a weak Carolean structure, you may wonder whether we also have a strong Carolean structure, and of course we do. So the reason for this is the following. As we mentioned in some lectures ago, in pseudo-Riemannian geometry, we usually introduce a derivative operator by the condition that it parallelly transports the metric. So this is the basic condition. We also implicitly assume, of course, that this guy is torsionless, which means that the covariant derivatives commute on any scalar function. But this is the basic condition that defines the compatibility between the covariant derivative or the derivative operator, you can call it whatever you want, with the metric. And this picks out a unique derivative operator in your pseudo-Riemannian manifold. It is important to recall that this operator here will be characterized by the Christoffel symbols, which are going to look like this expression here. Let me just so the Christoffel symbols for this operator here, and not for other operators, but for this operator, are going to, yeah, I'm calling them Christoffel symbols, but actually for other operators, they are called connection coefficients. They're only called Christoffel symbols for this operator. Anyway, the Christoffel symbols are given by this expression here. So we have a few derivatives of the metric. It's G sigma mu minus sigma mu. Okay. So this are the Christoffel symbols in a pseudo-Riemannian manifold. Now you see, if we want to do this in a degenerate with a degenerate metric, we run into trouble because this here is the inverse metric, and you cannot define an inverse metric for the degenerate metric because it is not invertible. Since it has a zero eigenvalue, it is not invertible. No inverses for H tilde. So we run into trouble when we want to do this. Can we define a derivative operator such that this happens? Yes, there is one. However, this is no longer unique. So we actually have this trouble in which we no longer have uniqueness of the derivative operator simply by choosing the metric. And this leads you into this weird situation in which you need to add more structure to your triple to actually get something that has a derivative operator, a well-defined derivative operator. So what we can define now is a strong Carolean structure, which is going to be made of a manifold, a degenerate metric, a vector in the kernel, and a covariant derivative. I'm going to add a tilde here because this covariant derivative is actually related with H tilde, so I want to keep it that way. So we're going to have this thing here, which is called a strong Carolean structure. So this is what we get. You have these two definitions. We have a weak Carolean structure, which includes only this first three guys here, and we have this strong Carolean structure, which also adds in a covariant derivative. So depending on what you're doing, you may be interested in one or the other. So it is not always, in mathematics, it's not always straightforward to know which definition you should use. So you end up using whichever one is the most convenient, whichever one is the one that leads you to where you want. So we have these two options here, and we will need to figure out which of them is the correct one. The correct one for us to discuss. And what happens here is the following. So suppose we are dealing with an asymptotically flat spacetime. We have an asymptotically flat spacetime MG. So this has an unphysical conformal extension, M tilde G tilde, and this extension, M tilde G tilde, leads us to a natural weak Carolean structure, square plus, induced symmetric, and vector M. Let me add the tensor indices here. So we get a weak Carolean structure directly from the definition. That is not an issue. The reason is because we can always define the induced symmetric. So you're going to define induced symmetric on the new hypersurface. That can be done. And this guy here is naturally given in square plus by this expression here. So this is just the derivative of the conformal factor. Notice this here is just the normal vector to the hypersurface square plus. Whenever you have a surface in geometry or even in Rn, you can define a normal vector. And in here, the normal vector for you might remember this from in my particular undergrad, it was in calculus 2. So a fact from calc 2 is that the gradient is orthogonal to level surfaces. And here, what's happening is precisely that. So square plus is a level surface with omega equals 0. So this here is the gradient, and the gradient is going to be orthogonal. It's going to be normal to that surface. What happens here as well is that since square plus is null, which is meant by saying that actually NA is null, it holds that NA is not only normal to square plus, it is also tangent to square plus. This is a weird behavior of new vectors, and you can notice this by noticing that NA is clearly proportional to NA, so they are tangent to each other, but they're also normal because NA actually vanishes. So they're both tangent and normal. This is a standard property of new surfaces, which may look a little bit unusual at first sight, but you get used to it. So whenever you have an asymptotically flat spacetime, you get a weak Carolean structure. It's going to be given by this triple here. You can discuss a strong Carolean structure as well, but this gets a little bit more subtle. It turns out to not be the most interesting definition. You're more interested in a weak Carolean structure, which doesn't have a preferred covariant derivative, which may be a little bit weird. So you don't have a preferred covariant derivative, but that is the correct structure you want to work with. So can we find a strong conformal structure, a strong Carolean structure? Yes. So the way you do this is the following. Suppose you have Mg, which is asymptotically flat, and it has a conformal factor omega. Now, this is one way of getting asymptotically flat spacetime. However, suppose you have the same Mg, but you consider now the conformal factor little omega times big omega, where little omega is a smooth function, which is everywhere positive. So it doesn't vanish. Now this guy here vanishes precisely at the same point as omega, so it has the same square plus, and this will still have a non-vanishing derivative at square plus. So this conformal factor works just as fine as this conformal factor. You can choose either one of them. Physically, none of them is preferred, because recall, what we're doing when we're considering conformal infinity is an unphysical construction. That is a mathematical construction. That is a mathematically interesting construction that allows us to describe infinity. But it is not a physical construction. So at least I don't know of anyone who believes that the conformal infinity is actually there. It is something that actually exists in physical reality. It is just a mathematical construction that is very useful for us to describe the behavior at infinity, to describe mathematically the behavior at infinity. And there's no physical way in which you could distinguish between this conformal factor and this conformal factor, because that is an unphysical construction. In particular, recall that M tilde, the conformal extension, typically doesn't even satisfy Einstein's equations with the same matter as the original spacetime. So we gave an example in which we considered Minkowski spacetime, and the extension M tilde is Einstein's universe. And this here is Minkowski, while this is an FLRW solution. So it is actually a cosmological solution which has a fluid content, and it has a cosmological constant, and it solves the Einstein equations for very different matter. So the physical scenarios in which either of these constructions appear are very different, but they are related by the conformal extension construction. And the meaning we give to this is that M tilde for the Minkowski spacetime is a mathematical construction that is useful for us to describe infinity. So this is not a physical construction, and in particular, there's nothing physical that can distinguish between these two choices of conformal factors. So either one of them is good. And what happens is that if we use this freedom in choosing little omega, we can impose to have a construction. We can always choose little omega in such a way that we get this condition here to hold. We can always get that the derivative of m actually vanishes. Yes, this is a minor comment that I forgot to make, but it's actually important in the definition. When we do this strong correlative structure construction, we also assume implicitly that the covariant derivative parallelly transports both the metric and the vector. So this is assumed, but we won't mind that much about it anyway. So we have this, and by choosing little omega in a convenient way, we can always impose this condition here. And this ends up leading to this condition here. So if you just use this condition on that expression for m that I wrote earlier, so you just use this, then you will find that we have this condition here. Now you see a general choice of omega, of big omega, doesn't need to satisfy this, but you can choose little omega in a way that this is satisfied. When this holds, then we have a strong correlating structure. But notice that this requires us to use this freedom in which little omega is free, and we end up needing to choose a specific little omega. So to get a strong conformal structure, we need to, what is the word I'm looking for? To give up on the freedom we have with little omega. So it is at the expense of the freedom we have with little omega. But we can get a strong correlating structure. What happens is that this freedom with little omega turns out to be very important to discuss symmetries at infinity. The freedom we have with little omega leads to a symmetry, and this is an important symmetry that we can't let go of. So working with the strong correlating structure to discuss symmetries ends up not being the correct decision, and we need to discuss only weak correlating structures which will not have the covariant derivative operator as something fixed. So with these comments made, we can now proceed to actually discuss symmetries at no infinity. That's correct plus. You have, of course, an analogous discussion to prime minus. You can choose either one of them to base your discussions in. They work exactly the same. So what do we want to call a symmetry at scribe plus? Now you see, when we make a construction, the construction we make to discuss infinity is we start with a manifold that we're going to say that it is entirely flat, and infinity is going to be defined in terms of the conformal extension m tilde, and this will lead us here to scribe plus. So this is how we define scribe plus. Now this construction leads us always to some triple scribe plus HAB and NA. So this is how we get this triple. So this triple always comes with the asymptotic flatness condition. So if we impose asymptotic flatness, we get something like this. How unique now is this triple? Because if we want to consider symmetries, that means essentially that we have more than one triple. So we can have different choices of triples, and they all represent actually the same thing. So they all are physically equivalent. So what is the freedom that we have when choosing these triples? And the answer is that we have some equivalence relation between different weak Carolean structures. And how is this equivalence relation given? The first thing is that whenever we do this construction, we better have the same underlying manifold, because we constructed this manifold, this scribe plus manifold, in such a way that it should always be diffeomorphic to R cross S2. So this is the only manifold that we can have up to diffeomorphism. So we needed this thing here to be equivalent first to the same manifold. Now, what is the freedom we have on changing H tilde? And the answer for this comes from the freedom we have in changing G tilde. And G tilde is given always by omega 2 G. And the freedom we have in this is by redefining omega 2. Redefinitions of omega 2 will always come in the form, and this will be equivalent to G tilde equals little omega 2, big omega 2, G. So we can multiply by little omega 2, and we will get something that is physically equivalent. Because both of these metrics are unphysical, so we can just change the conformal transformation, and that doesn't change anything physical. This means that the freedom we have in H tilde AB is that it can suffer, it can undergo a conformal transformation to little omega squared HAB tilde. So this is the freedom we have for changing the metric in the square plus. And at last, we have the freedom changing n. And what exactly is the freedom we have when we're changing n? Well, since n is given by that expression I wrote earlier, it's given by this expression here, you can just carry out the calculations when you change G tilde from this to this, and omega from omega to little omega times big omega, and you will find out that the transformation for n ends up being omega minus 1 times n. So we have that these two triples should always be seen as physically equivalent, which means that any transformation that takes this triple here to this triple here is a symmetry transformation. So the symmetries at no infinity are precisely the transformations that take this triple to this triple. How can we discuss what are these transformations? In my opinion, the simplest way to figure out what are these transformations is the following. You choose what is going to be your canonical or your reference triple, and then you figure out what are all the other possible triples in terms of this guy. So you choose a canonical reference triple, and then you consider all the other triples that are possible, and the transformations between the triples end up being the symmetries you have available. So we need to choose a standard reference triple. How are we going to do that? Well, we know that up to diffeomorphism, the manifold is always going to be R times S2. So this is the manifold we will consider in our standard triple. Next, we need to decide on what is the metric. Well, we earlier used a coordinate approach within Schwarzschild spacetime and found that the metric we got was something along these lines here. Now, this works for Schwarzschild, but does it work for everything? And the answer is yes. It can be shown, and this is done, for example, in Wald, chapter 11, which is a chapter on asymptotic flatness, that you can always choose coordinates so that the conformal metric close to infinity is given by something that looks like this expression here, plus corrections of all the omega. Some authors actually prefer to define what is an asymptotically flat space in terms of these conditions here. So some authors prefer to impose that there is some coordinate system near infinity with certain decay properties of each component of the metric, and use that as a definition for asymptotic flatness. This in particular is what Bondi, Metzner, and Sachs did originally in the 60s, but later Penrose introduced the conformal compactification method, which I consider to be, at least in the applications I've seen so far, the most mathematically sound and more mathematically interesting. And it ends up to be useful for proving theorems. But there are some scenarios in which you may want to use this metric decay properties depending on what you're doing. So it's again what I just mentioned a few minutes ago, that when you're doing math or even when you're doing physics, you need to figure out which definitions are appropriate to the problem you're handling. And depending on your physical scenario, depending on what you want to get, you may want to use one definition or another, and some of them might turn out to be equivalent. And I do think that the original definitions by Bondi are equivalent to, within, of course, the reasonable assumptions, are equivalent to Penrose's definition, but I don't recall all of the details about this. In any case, you can always choose, when you use the definition we gave, you can always choose coordinates such that this thing here holds. And this means that the induced metric at scribe plus can always be taken to be DS2. You can always choose coordinates such that these hold. So this is selecting a standard triple. Is this the only possible metric? No, because as I said, we can have, for example, conformal transformations that release a different metric, but it preserves the conformal structure. And what we have in this case is a different metric, but it has the same conformal structure. So physically, it means the same thing for us. And the reason it means the same thing is because we are dealing at infinity. So we are free to do these transformations. But for a standard reference triple, we can take the round metric on the sphere. And at last, we need to discuss what is going to be the vector NA. And in this choice of coordinates here, NA is given by the derivative along the u direction. So our standard triple, standard reference triple, is going to be given by R cross S2 with the round metric on the sphere and by the vector DDU. Okay, so this is the standard reference triple. Now we start discussing what are the transformations that we can do on this triple to get it to a triple that is related to it in this fashion here. So we will go step by step. We will preserve one structure at a time and just go imposing more and more conditions until we get to the final result we want. So the first step is the first condition we want to impose is that I plus is preserved. So this here means that we are preserving the underlying manifold, which means that the transformations we can consider are diffeomorphisms. So all valid symmetries at no infinity need to be diffeomorphisms because we need to preserve the manifold structure of no infinity. So that gives us the possible symmetries. It doesn't mean that all of these guys are symmetries, but the possible symmetries all live in the space of diffeomorphisms of R cross S2. So this is an upper bound on the possible symmetries. The actual symmetries live in a subset of this guy. So, but this is the largest option we have so far. Now we need to impose that these things are not only diffeomorphisms, but actually preserve the conformal structure, which means that they preserve this equivalence relation here. They all have within this limitation. So they can only transform the metric up to a conformal change, up to a conformal transformation. So we need them to transform the metric in this very specific sense. This means that they are not only diffeomorphisms, they're actually conformal isometries. And how do we figure out which transformations are actually conformal isometries there? And the way we can look at it is by taking a look at the metric. So the metric, the standard reference metric that we chose is the round metric on the sphere. So this guy here can be transformed to some conformal factor times the same round metric. But this here are the conformal transformations conformal transformations of S2. This, however, refers only to theta and phi, not to u. So as far as theta and phi are considered, but not u, the possible transformations live in SO plus 3,1, which is the conformal group in the sphere, as we saw in the last lecture, which is, of course, the Lorentz group. So notice that to get this invariance here, that to get this group of symmetries, we needed to have this conformal factor. If we had chosen to work with the strong conformal structure, we wouldn't have this freedom, and we wouldn't have SO plus 3,1. Instead, we would have only SO3. And this thing here is extremely important because we need to get this guy. This guy here is the Lorentz group. So the Lorentz group at infinity will appear only because we are preserving the weak Caroline structure and not the strong Caroline structure. If we were preserving the strong Caroline structure, we would lose a bit of SO plus 3,1 and would get only SO3, which means we wouldn't have boost symmetries at infinity. So you see, the correct structure to consider at infinity is the weak Caroline structure and not the strong Caroline structure. And this can be seen by this argument. You need omega 2 to appear here so that you actually get conformal transformations of S2. But this is not the full group yet that we get at this point. We also have a larger factor, which is going to be the following, which we still can have smooth functions on R times S2. So this thing here is the portion that corresponds to transformations on theta and phi. This here corresponds to transformations in U. Why? Because the transformations that we can have here are all Möbius transformations. So the transformations between theta and phi all have the form of a Möbius transformation. And these transformations live precisely on SO plus 3,1. This guy here, however, can be transformed according to any transformation that looks like this. Looks like a smooth function that takes one real value u, which is the original value u, and two angles. And we assume that df du is positive because we want to map the whole values of u to all values of u. So we want to preserve that this mapping is from the real line to the real line. So we need this condition here. But we have any function, and these functions here live in this space. So as a set, not as a group, but as a set, we can write the set of transformations that we have so far as this thing here. To figure out what it would look like as a group. So for example, to know whether it is a semi-direct product or if it is a different notion of product, or if it's neither, we would need to know more details about the group structure, which I'm not writing right now. But the actual group of transformations that we get at this stage is called the Neumann Unti group. So this is another group of symmetries at infinity, but it does not preserve everything that we wanted. So this group here is extremely large. So it has all of this freedom. They have this freedom, which leaves on the whole space of smooth functions on R cross S2. Why are these functions smooth? Because we are assuming that we're working with smooth manifolds. And since we're working with smooth manifolds, the transitions between charts should be smooth functions. So due to these conditions, due to this hypothesis that the manifold is smooth, we need to have smooth functions in here. So this is the group we have so far. But this is still not the end of this discussion, because you see, We're only preserving the conformal structure. We're not preserving the weak Caroling structure, which is what actually needs to be preserved. So we need to impose one extra condition. We need to impose now that square plus HAB and A is equivalent to the transformed version, which is going to be square plus omega 2 HAB tilde, omega minus 1, and A. So we need this equivalence to also hold. And this is going to restrict our transformations even further. So now, instead of preserving only the conformal structure, instead of dealing only with conformal isometries, we're going to deal with a smaller class of transformations. And what exactly will these transformations be? We have here that n transforms in this way, but notice if you go back in our discussions, you will see that the parameter u should always be related to n, such that this expression here holds in the n-physical spacetime. So this here holds on m tilde, because we don't really have a preferred it is no okay, yeah, this doesn't matter really. While you don't have a preferred covariant derivative on square plus, this here can be thought of in square plus, because this is acting on a scalar, and covariant derivatives acting on scalars always give the same result. So this here you can write in this way if you want, but you can also write in this way, and it's perfectly fine. So it will always have this condition here. This condition here always needs to hold. This is the definition of this guy here. And what exactly do we get from this? If we transform this expression, this will give us that omega minus 1 and A times a transformed version of this guy here. This here is a prime, so it just indicates that we're taking the transformed version. This is going to lead to 1, which means that dAu needs to transform in the following form. We need to have the dAu is taken to omega dAu. We can write this in a slightly different way by writing that we must have that du is taken to omega du. Okay, this symbol here makes sense. It is differential form notation, and it means essentially the same thing as this here. So you can just write like this. Okay, so this is the basic definition for the symbol. So we're gonna have this construction here, and we can now integrate on both sides to find that u must be taken to omega u plus an integrating factor, which can depend on the angles. So this is the most general transformation for u that preserves the weak Caroling structure. This omega here has a well-defined expression because omega is completely defined by the Möbius transformation, since we already fixed it by doing this analysis here with the conformal structure of the metric. So omega is fixed by the Möbius transformation on the metric. And what we get at last is that the most general transformation that we can have for the angles and for u is going to be a transformation with the form zeta goes to this expression here, which is just the Möbius transformation. This is just the most general conformal transformation on the sphere, and u, the most general conformal transformation on the sphere that will still preserve the weaker Caroling structure, will be given by an expression like this. So I just changed from spherical to stereographic coordinates from this equation to this one. So this is the most general transformation. This omega is completely determined by these constants A, B, C, D. And this is the most general transformation that we get. This here is what we call a boundary Metzner SOX transformation. So this is a BMS transformation. And these are the most general transformations that preserve the weak Carolean structure. Something that is important to notice now is the following. How do we characterize these transformations? Well, we characterize them completely by a Möbius transformation, which is going to determine this guy and this guy, and by a function on the sphere, which is going to determine this guy. So the BMS group, the group of BMS transformations, as a set, is going to be given by what? By a Möbius transformation, which is, as far as groups go, as far as Lie groups go, the same as a Lorentz transformation, and by a function on the sphere. Smooth function because we're dealing with smooth manifolds. And notice that we no longer have that R factor from the Neumann unity transformation because the U dependence is now fixed in the transformations that we can take. So this is the set structure of the BMS group. Now you can work out the transformation laws for this. If you the composition laws, I'm sorry, if you consider the composition laws of the transformations. So what happens when you do zeta goes to zeta prime? Sorry, let's write in this right. U zeta goes to u prime zeta prime, and u prime zeta prime go to u double prime zeta double prime. Then you consider what happens when you do this. You find out that the composition rules will be given by this law here. So lambda is the Lorentz matrix. F is the element of the space of functions, and they're going to compose in this complicated way here. So plus this is the omega associated with the inverse of lambda, and this is composed as a function with lambda. Then this is multiplied as a scalar with this other function here, which is a composition of f prime and lambda. So this is a little bit complicated, but what is really important here is the following. First, we can define the subgroup L lambda 0, where lambda lives in SO31. And this guy here is, of course, isomorphic to SO31. So we have a copy, at least one copy of the Lorentz group inside a BMS group. On the other hand, we can define another group, another subgroup T, which is going to be the identity paired with any function, where F lives in infinity of S. And of course, this guy here is going to be isomorphic to infinity S2. So we have these two interesting subgroups of the BMS group. What else do we have about them? The first thing is infinity S2 is a normal subgroup of the BMS group. So this is the first interesting thing. Next, if you use that group product I just wrote, you will notice that it happens that lambda f can always be written in the form lambda 0 composed with 1f. So a general BMS transformation is always one of these function transformations followed by a Lorentz transformation, which means the GBMS can be written as SO31 times infinity S2. Notice there's still not a product symbol here. This is just the factory. So you can first do this transformation and then you do this transformation, and this gives the most general BMS transformation. So this is what we get so far. Finally, you can also notice that the intersection of these two groups is actually the identity of the BMS group. And these three conditions the condition that C infinity of S2 is normal, the condition that the group factors in this way, the condition that the intersection is just the identity, means that the BMS group can be written as a semi-direct product between these two groups. This is the space of the group, and the group product is additional functions. So you operate on two elements of the group by addition, by pointwise addition. We should compare this guy here with the Poincare group. The Poincare group had this appearance here. So you see that the Lorentz group appears in exactly the same way, but in the BMS group, we have this much larger group than simply the translations we had in the Poincare group. So this is the first indication that we have that it is fair to call these guys here super translations. And now to understand how exactly these guys are super translations, how exactly these guys go beyond the usual translations, and why exactly this guy can indeed be thought as the usual Lorentz group, we need to go to another description. We need to go to a better, to another formalism to see how exactly all of these guys fit together. So let me now give you an alternative derivation of the BMS group by using killing fields. So now BMS through killing fields. So now how we do each step. First of all, we want to preserve square plus. And this here is automatic because as long as we are imposing that we have killing fields, the killing fields will of course be, these are actually conformal, sorry, conformal killing fields. These are actually going to be, the transformations that the killing fields generate will be diffeomorphisms. So there's nothing to worry about this. The next step is to preserve the conformal structure. But I'm going to go straight and just preserve the weaker Roman structure and write both conditions at once because it is a bit easier to see them together, I think. Weaker Roman structure. And what we're having is that the killing fields that we're working with, which I'm going to call psi, must have the following properties. So they must transform HAB in a conformal manner. So they should have this appearance here. Meanwhile, they should always also transform NA in a specific way, which will be minus lambda over 2 NA. Why exactly am I choosing this conformal factor here for NA? The reason is because HAB goes to omega squared H, while N goes to omega minus 1 H. So I'm just flipping the sign so I get this minus 1 here, and I'm dividing by 2 so that I get the fact that this guy here is to the power of 1, while this guy here is to the power of 2. The reason I can just flip a sign rather than invert lambda here is because we're dealing now with infinitesimal transformations. So now we need to think of these omegas as being something like omega equals 1 plus, it's actually a factor times lambda. So when you expand these guys here, you're going to get something that looks like H, let's say H prime, which is the new H, is going to be the old H plus a minor correction here. Alpha has to be over 2. So we are going to have here something that looks like this. So lambda is related to omega in this particular way. And then we get these two expressions here. Now, we can now impose these expressions to figure out what are the possible psi's that satisfy these conditions. So this here are differential equations for this field psi. And solving these differential equations will tell us what are the possible psi's that actually lead to symmetries of no infinity. So let's solve each of these in sequence. We start with the condition on the metric. The condition on the metric is telling us that this here holds. Sorry, I'm going to actually use a different operator. I'm going to use a generic operator. I'm not going to use specifically the, how do I say it? I need to specify which derivative operator I'm using. I'm going to use the derivative operator dA, which is the derivative operator on the sphere. Now, notice that I'm going to consider this as an operator on R times the sphere. How can I do this? What I'm going to do is I'm going to define that the Christoffel symbols with zeta, etc., are the same as the operator on the sphere. And if there is any u here, I'm going to define that this is 0. The u can be anywhere. So this is the definition. I'm going to impose that the Christoffel symbols with only angular variables are the same as in the sphere, and that the Christoffel symbols in which at least one u appears all vanish. So this is how I define my operator dA. Now, using this operator dA, what exactly do we get? The expression on the Lie derivative is going to look something like this at first. We can now open this Lie derivative by using a differential operator. And then we have that complete definition that I gave earlier, which is going to look in principle like this here. This is without simplifying the expression, because we made a lot of simplifications along some of the lectures by assuming that the derivative operator was compatible with the metric. Now, I'm working here now with something that is slightly more general, so I'm writing it out explicitly. But in the next step, we can simplify it either way. And what we will find is the following. So this here is B, I see. Okay, so for this particular derivative operator, I could have worked with another one. But for this particular derivative operator, this guy here will vanish because these two guys actually commute. And the reason is because HAB is the round metric on the sphere. So they end up commuting, and we can write this thing here as simply HCB tilde psi c plus dB HAC tilde psi c. So this here is the expression. Now, psi is a general vector on square plus. We can decompose this guy here. We can decompose psi as being a vector YA on the sphere plus some function times NA. So this here is the component on the sphere. This here is the component along the direction up. We can decompose it in this way. And in particular, it holds that H AB psi B equals YA. So we have this relation between them. This here is just a general decomposition that we can make. And this here is what we get when we project the vector into the sphere. So notice that what this equation here is telling us is that this y component of psi obeys this equation. YB plus dB YA. So this equation is satisfied by YA. However, all of these, all of the objects that I'm writing in here are defined in the sphere. So I can consider this as an equation on the sphere. And this tells me this is precisely the expression for a conformal killing vector on S2. So YA is a CKV on the sphere. This solves part of the problem. This tells me 1/2, so to speak, of the behavior of psi. Furthermore, since this equation here holds on the sphere, it turns out that in the sphere, H tilde has an inverse because the sphere is a Riemannian manifold. So when I'm considering this equation on the sphere, this guy here has an inverse, and I can tell you that lambda needs to be given by dA YA. This is just the same argument we did a few lectures ago when dealing with the conformal killing vector equation. The general expression would be 2 over n, where n is the dimension of the manifold. But here, the sphere is a two-dimensional manifold, so n is just 2, and we can ignore that. So we found an expression for lambda. Notice as well that since YA doesn't have any non-vanishing components along the u direction, and neither does dA, it turns out that this expression here holds both, holds on S2 and on square plus. So you can write this here in either of them. It holds in both of them. This is one part of the problem. So far, the calculations we have done consider the conformal structure. So they impose that the transformation preserves the conformal structure. So it preserves square plus, and it preserves in a conformal way HAB tilde. Now we get to preserving the weak Carolean structure. So impose the remaining condition, which was that minus lambda over 2. We now know what is this lambda, but we impose that minus lambda over 2 NA equals to the Lie derivative of NA along the direction of psi. And what exactly is going to be this expression here? So how do we open up this expression? We can use the definition of the Lie derivative for a vector, and it is given by, in terms of an arbitrary derivative operator. I'm going to choose still the same operator, dA, because I find it convenient. And I'm going to write it in this way here. So this is how I choose to write it. Now, what do I have here? Since D does not have any components along the u direction, this guy here vanishes. And what I get is simply minus NB dB psi A. So this is the expression I have so far. I can rewrite this, just drop in the sign, and I can rewrite this here simply in this way, just improve notation a little bit. So we get this expression. But now I can open up the expression for psi, because I know psi is given by a piece that is y, and by a different piece that is f and a. Now, what do we have here this time? Let me just okay, yeah. Here we are contracting dB with NB. And this will imply that when we open up the expression in Christoffel symbols of this whole guy here, then we're going to have only an expression that looks like this. We'll have NBdB YA. This here is actually DU YA. And this is given by DU YA plus the expression with the Christoffel symbols, which is going to be UC C. Okay, so you have this thing here. Now this term vanishes because YA is only defined on the sphere, while this guy here vanishes because we have a U in the Christoffel symbol. So all this guy here vanishes. Let me erase this draft, and we get only NB dB. Let me use a product rule here. F and A plus F NB dB NA. Okay, let me check my notes. Okay. It will follow also this guy here ends up vanishing, partly because of the Christoffel similar question. No, let me just go back here. No, yeah, the reason is that actually when you use this specific choice of covariant derivative, it holds that it parallelly transports NA. You can just check this if you want, but this choice will always lead to this. And in fact, it is something even stronger than this. What holds is that, in fact, square plus HEB NA DA is a strong conformal structure. This sort of construction is actually the most one of the main examples of strong conformal strong Carolean structures. I'm sorry, I keep mistaking conformal and Carolean when I'm speaking. And this is in fact a quite general construction. You can have to get a strong Carolean structure. You can take, for example, R times sigma, where sigma is a Riemannian manifold. You take the metric to be the metric on the Riemannian manifold. You're going to take NA to be the vector along the remaining direction, and you're going to take the covariant derivative to be the covariant derivative D on the Riemannian manifold. So here, this is a very general example of a strong Carolean structure, and this is exactly what is happening in this scenario. So this guy gets away, and what you get here now is NA NBDB F with this other thing here. So we now use this part and this part to see that we got to lambda over 2 NA equals this thing here. Now, if we just see that these two terms are parallel, we see that what we actually have is that this guy is equal to this guy. So lambda over 2 equals to NB dBF. But we know that this guy here is actually dAya over 2, and that this guy here is just the derivative along the direction of u of f. So we actually have this equation here. This is going to be a differential equation, of course. And we can solve this equation by noticing that this guy here does not depend on u. And we find that the general solution here is going to be the f equals to u plus, f equals to dAya over 2 times u plus some integrating factor that I'm going to call g of zeta, some integration constant, sorry. I'm going to call g of zeta z bar. So we get this thing here. When we take this all back to the general expression of psi, we find that psi is given by a conformal killing field on the sphere plus a factor that looks like this. Now I'm writing this as G rather than F. I used F for the transformations earlier because this G here has a different normalization. It doesn't have this dAya normalization in front of it. And you actually need to be a little bit careful when translating between between both formalisms. So I'm just going to write it in this way. Now, to figure out how the BMS group relates to the Poincaré group, we are going to take a look at each possible transformation that we have inside here. So there are two general options that we will have in here. No, actually, three. So there are three stereotypical examples we want to consider. The first case is when G vanishes. In this case, we have psi equals Ya plus dAya u over 2 NA. Oops, sorry, I'm using A in two places here. It's better to write it like this. So this is one of the possibilities. As a subcase, as subcases, we're going to have dB by B, not 0, and dB by B equals 0. This here holds if Y is a Killing field. And the second case is when YA vanishes, in which case the vector is given purely by G, zeta, zeta bar, and A. Okay, so we have these two scenarios here, and in particular, this one has two step cases. So how do we interpret each of those guys? We start with the first guy. So a calculation that you can do is you can grab those expressions I wrote a while back for the generators of the Poincare group. So I had that, for example, it was, if my memory doesn't fail me, we had, for example, this guy here. This is one of the generators of rotations. Y d zeta A. Maybe I'm missing a minus sign here somewhere. So this guy is plus or minus jz. I'm not sure which of them. So we have this guy here, and we want to know how this guy appears at future no infinity, because we want to compare it with the vector that we just found for the BMS transformations. So this here are vectors in square plus. This here is a vector inside of 4. So how do we get this vector to square plus? And I'm not going to open this calculation here in particular because I did it with Mathematica. It is complicated to get all the transformations right, but it's not too complicated. But I'm lazy enough to not want to do it here. So the way you do it is you start with this vector in these coordinates. Then the first thing you're going to do is you're going to change Cartesian coordinates to spherical coordinates. U, R, theta, phi. Or you can use stereographic coordinates if you prefer. So use whichever one you want. So we first do this. Then the first step is drop the R component. And the reason is because you will want to consider the vector on the induced you want to consider the vector on the submanifold. You want to consider the vector on scribe plus. So any components along the direction of the radius are not really relevant. You will just project them away. So what you want does not include the R direction. So you drop the R direction. And then you take R goes to infinity. So you take this procedure here, and you find what is the expression of Jx on future no infinity. Analogously, you can do this, for example, with a boost. So a boost is going to be given by something that looks like this. This one, I know the signs because the signs are quite simple. Everything is a plus. So you can also get the boost. You do the very same procedure, and you can find the boost at future no infinity. When you do this with rotations and boosts, in Minkowski, and you can do Minkowski because you actually want to compare with the Poincare group, and the Poincare group is defining Minkowski. So this is fair. Now, what you get when you do rotations and boosts at square plus, and starting from Minkowski spacetime, you're going to get a general field, a general Killing field that has this appearance. It's going to look something like this, where this guy is a CKVN sphere. Again, I'm writing of the young for the wrong indices here. So this is the expression, and of course, this is precisely the expression we had for the BMS transformations. So indeed, and notice that this expression here came from the conformal Killing fields on the sphere S2. So indeed, the SO plus 31 factor that we had, the Lorentz group factor that we had, is indeed the Lorentz group. That is indeed what we would expect, the Lorentz group that we get from Minkowski spacetime. The two subcases I mentioned, which refer to whether or not this here vanishes, are the following. If it vanishes, then we're dealing with Keeling fields on the sphere. And this is SO3. So these are actually rotations. So this vanishes. If this doesn't vanish, then this is a conformal Keeling field that is not a Keeling field, which means these are boosts. The boosts are not a group in 3 dimensions. The set of all boosts does not make up a group. And the reason is because when you compose boosts along different directions, you need to have a rotation. And this is intended to keep the total velocity from exceeding the speed of light. So you have this restriction on the structure of boosts along different directions. Boosts along a single direction do make a group. But when you are in more dimensions, you don't have this group structure. But you do have that the rotations still make a group, which is SO3. And the full Lorentz group is going to make SO plus 3,1, which in here appears at infinity from the conformal transformations on the sphere. So this is one part of the story. We still need to discuss translations, which are actually the most important thing, the most interesting thing. And the other thing that we can do now is the following. So consider we have here some of the momentum vectors, some of the translation vectors, P mu. These guys here were given by these expressions here. So these were the expressions that we got for them. Now, you can consider all of these guys at no infinity by doing the same procedure. So what you're going to do here is just you change coordinates to u zeta bar. You consider these guys here. Then what you do is you drop the radial components. I think these guys here don't even have radial components. I think the radial components only appear in the boosts. But anyway, if they do have a radial component, you drop them. I don't recall it right now. It's been a while since I made these calculations. After you drop the radial components, what you do is you take the limits in which r goes to infinity, of course, while holding u constant. So, and then what you get is the expression for these guys. And what do they look like? What they look like, this here is at square plus, is going to be, let me write it with the same notation. It's going to be something with this appearance here. This is DDU. What is F tilde? F tilde is some linear combination of spherical harmonics with little l ranging from 0 to 1. So what you have is going to be something like this here. Yeah, I think I'm writing the wrong. Just write it like this. They're going to have something like this. The case L equals 0, which implies M equals 0, is actually the time translation. The case L equals 1, which has M equals -1, M equals 0, and M equals +1, refers to the spatial translations. So this is the expression for a translation, a time or spatial translation at future no infinity. And what is the expression that we found for the BMS group? With the BMS group, we found this expression here, where G is a function, any smooth function on the sphere. So what we have for BMS, what the guess is psi A equals G zeta bar ddua, and G this time can be written as a linear combination of as many spherical harmonics as you want. So you see, this is how they relate. these guys here, the translations only go up to L equals 1. These guys here go up to any value of L. L can go to infinity, and that's fine with them. So this is why we call these guys, these transformations, super translations. They're super translations because they generalize the translations. Notice this has nothing to do with supersymmetry or any of the other concepts in physics in which people use the word super. So super in here just means that this is an extension of the translations. These are not only, they are something that algebraically, when you look at the group structure, they look a lot like translations, but they are different. They are something that goes beyond translations. And whenever people discuss super translations, they usually write a Penrose diagram. They make it a sort of rotated diagram, which looks something like this. So this here is Minkowski. So what I did is I just took the diamond diagram and rotated it. So this shows one extra spatial dimension. And something that is problematic in this diagram is that actually this thing here in yellow, which is spatial infinity, is actually a single point rather than a circle. But anyway, we pick this guy here, and the super translation is something that at infinity will translate each point by a different amount, because the super translation depends on the particular angle that you are doing the translation. So it is going to do something like this. They usually draw this picture in which you see that the super translation is doing a different translation at each direction in what we call the celestial sphere, which is the sphere at infinity. So you have this generalization of the concept of translation. And this is the way in which the BMS group relates to the Poincare group. This is how they both are related. So you see, let me write these guys again. So we first had the Poincare group, SO plus 3, 1, semi-direct product with our 4. And now we have the BMS group, which is SO plus 3, 1, semi-direct product with the group of super translations. So now these guys here are the Lorentz group. So they do have Lorentz transformations in there. This guy here are the translations. But now we have super translations. And recall what I mentioned earlier. The structure of a semi-direct product already tells you that. But super translations, just to make it even more clear, are a normal subgroup of the BMS group. If you recall the discussion I made about normal subgroups, this means that the super translations are a unique subgroup of the BMS group, in the sense that you sort of have only one copy in there. Now, let me remember this. It's been a while since I read that paper. Yes, you have. It is in the work by Sachs. So it's in one of the original papers by Sachs. Yeah, it was in 1962-ish. So maybe a little bit after, a little bit before, but I think it was 1962. And he discusses all of the structure, and he proves that the only four-dimensional normal subgroup of GBMS are the translations. So the translations are a very specific subset of the BMS transformations. If you gave me, if you mixed up all of your notation, you used a very weird notation, or you just gave me a list of all of the possible BMS transformations, this will of course be not only an infinite list, but an uncountably infinite list, so that even the concept of list sort of breaks down. But it will have this ridiculously large list of transformations and how they relate to each other algebraically, it would be possible for you to tell which of these transformations are translations. So you can select what are the translations inside the BMS group. And that is because they established the only four-dimensional normal subgroup. You can still tell which transformations are super translations, but you cannot tell which of them are pure super translations and which of them are mixed with a translation. So which of them are exclusively new super translations, which of them are super translation plus a translation. So you do have this weirdness in that, if I recall correctly. I remember that Sachs discusses this point very precisely, but I may be mixing something up with this super translation in Níckolas. Translations definitely are unique. I'm completely sure about that. And there is the other interesting issue, which is, what about Lorentz transformations? Are Lorentz transformations unique? And the answer is a very resounding no. So SO plus 3,1 is not a normal subgroup of GBMS. So what this means is no preferred Lorentz subgroup. What does this mean? This means the following. Suppose you start with Minkowski space. So you start with Minkowski space. It looks like this. And then you know what are the Lorentz transformations. And here, when you get to infinity here, you still know what are the Lorentz transformations. They're just the limits of the transformations you had in the interior. So, for example, you're just going to take gx as I defined earlier. You take the limit as r goes to infinity, and you're going to get to the correct rotation at infinity within the BMS group. So that is not an issue if you're dealing with Minkowski spacetime. Now, suppose instead that you're working in a much more complicated spacetime, but that is still asymptotically flat. So let us consider, for example, a star where a spacetime with a collapsing star that collapses to a black hole. This is the Penrose diagram for the star. You have here the collapsing star. It's the region I'm shading. This is the star. This dashed line here is the event horizon of the black hole. And this here is a non-stationary spacetime. So this is a very complicated spacetime. The specific metric of the spacetime is very complicated, and it doesn't really matter for us in here. What matters is here you have Scri plus, and at Scri plus you have GBMS. Now you take this copy of GBMS. So you take BMS in this spacetime, and I ask you, what are the Lorentz transformations? And the answer is, you have no idea, because there's not a preferred definition of the Lorentz group inside the BMS group. Algebraically, you can't tell which transformations are Lorentz transformations. If you messed up your notation, you just gave a list of all of the transformations and their algebraic properties and asked, which of these are Lorentz transformations? It is impossible to answer that, because the Lorentz group is not a normal subgroup. You have multiple copies of the Lorentz group inside the BMS groups, the BMS group. Why is this relevant? Why am I talking about this at all? Why am I so interested in these uniqueness properties? And the reason is they are physically significant. This may look like just mathematical abstraction, but it is actually physically significant. Because you see, when you're dealing with asymptotically flat spacetimes, you have many interesting notions that you can do in general relativity. So for example, suppose that you have a spacetime that has some object here in the middle. It could be a black hole, it could be a star, it could be anything you want. It could be a galaxy, it could be a planet. And you go here close to infinity, and you want to know a few questions. So for example, what is the mass of the spacetime? What is the mass of all objects contained in spacetime? In particular, this guy here. So what is the mass? Furthermore, what is the momentum? So we can just merge this with the mass question and ask, what is the form momentum? We can go even further. We can ask, what is the angular momentum, which in relativity is actually a tensor, because it mixes, essentially because you have to mix the rotations and boosts together, and you get this more complicated structure, which is a tensor. So what is the angular momentum of this guy here? And you have a bunch of definitions. So when you're dealing with asymptotically flat spacetimes, you can get these definitions of what is the mass, what is the momentum, what is the angular momentum. And there are two main definitions that are interesting. One of them is the ADM construction, which goes after Arnovitz, and Misner in a series of 12 papers from 59 to 62, if I recall correctly. So it's ish. And they have these definitions of mass and momentum, and I believe angular momentum as well, at spatial infinity. So what they do is they have their diagram here. You're going to have some Penrose diagram, and it's asymptotically flat. So to my experience, this is more of a folk theorem than but this doesn't mean that I don't know a rigorous proof, but I believe it to be true. And I'm sure if someone looked into it, I just never looked into it. But whenever you have an asymptotically flat spacetime, you have this diamond structure in the Penrose diagram. So I drew the diagram for the collapsing star. It looks like this. Minkowski looks like this. Schwarzschild looks like this. If you consider more complicated black holes, you can get a structure that has a lot of these guys. So this, for example, is Reissner-Nordstrom spacetime, and you just have many copies of this here. And each of these is an asymptotically flat region. So these diamonds usually represent, if not always, asymptotically flat spaces. So you have this region here, and their construction it happens here. So they define the so-called ADM for momentum at spatial infinity. And if I'm not mistaken, I'm quite certain of this, that they also have an angular momentum construction. I just don't recall it right now, but I think they do. And this here is going to give you a measure of the form momentum in the spacetime as measured by a spatial slice. So you're going to have this spatial slice that eats everything in the spacetime and tells you what is, for example, the mass. This can or not be interesting depending on what you're doing. Because, for example, suppose you are considering a stellar collapse or a black hole merger. A black hole merger is even more interesting. So I have here your black hole merger. So you start here with your two black holes, and eventually they merge together, and somewhere in the middle, they emitted gravitational waves. Now, what happens is that the ADM mass cannot measure the mass without the gravitational waves. It will always, you can choose different slices here, but it will always have all of the mass in the spacetime at a single time. So it includes both the mass of the original black holes and then the mass of the black holes plus the gravitational waves, and then the mass of this black hole here plus the gravitational waves, and so on and so forth. It always gets the gravitational waves. And this can or not be interesting depending on what you're doing. In some situations it's interesting, in some situations it's not. So a different notion of mass is the boundary Sachs mass, or simply boundary mass. This here is another definition that considers instead measurements by taking at new infinity. So instead of taking this spatial slices over here, they take new slices coming from new infinity. So they measure mass like this. And what happens this time is that you have here your black holes, and this gives you this mass at this point. And then you have here the black holes, which emitted some gravitational waves, but these gravitational waves move across new geodesics, so they're not caught in this line here. So now you have a mass 2. And then you have the final black hole, and you had more gravitational waves in here, and you have a mass 3, and so on and so forth. So the boundary mass can measure these things. You can also define a boundary for momentum, but no boundary angular momentum. So you do not have a good definition of what is angular momentum and no infinity. And the reason is precisely because the Lorentz group is not uniquely defined. An angular momentum, if you've heard of Netter's theorem before, Netter's theorem is a result in classical mechanics and field theory that says that to every symmetry there is a conservation law. And to every conservation law, there is a symmetry. So for example, energy is related to time translation. Momentum is related to spatial translation. And in relativity, angular momentum is related to Lorentz symmetry. So the issue here with angular momentum at no infinity is the fact that since the Lorentz group is not unique, you don't really know which Lorentz group you're talking about when you want to define angular momentum. And you have this difficulty in defining angular momentum at no infinity. So I consider this to be something quite physical. So you see that the algebraic structure of the BMS group also leads to this very physical statement that you have difficulty in defining what would be angular momentum at future no infinity. Some people refer to this as the angular momentum problem in GR. But some authors prefer to think, as I do, that this is actually a feature, not a bug. And this shows how the BMS group can be interesting, even when you're looking just at the group structure and at the very basic things about BMS symmetries. It does happen, however, that it has many other constructions and interesting properties that we can use on other areas of physics, which of course need to involve gravity. So we can look after at other applications within classical general relativity, but also to applications within quantum gravity and quantum field theory in curved spacetimes, which is going to be a goal for the next lecture. Consequences in applications. So this is what I have to tell you for today. If there are any, I'll take questions now. Okay, there doesn't seem to be any, so I'll stop recording and ask again.